So welcome to the second lecture today. So I hope you managed to get the PDF and the keynote versions of the lectures of the course site yesterday night. There were no PDFs on the site until yesterday, so that's why if you try to download it, you got an error because there just was nothing there yet. It's up now. There are also the slides for today up, and as before, download them after the class if you want to have something, to keep it, because most likely they will change a little bit between what you're seeing now and what will be the corrected version afterwards. Okay. The other thing is, were there any questions from Monday? Okay, so we managed to reduce the number of people in the audience already quite a bit. Probably everybody who wanted to see equations and is now frustrated. Well, okay, don't worry. We'll get some equations today. One thing is, I probably looked a little bit high level in the sense that, okay, we talked about, what, active learning, reinforcement learning, and so on is. And these concepts were explained in a moderately high level conceptual manner. It's actually important that you remember those things, because quite often this is where you can get a lot of leverage in practice if you need to solve a specific problem. Okay. So this is probably the only time where I'm asking you to, just make sure you remember those various concepts of, what you can do with machine learning. Everything else, I mean, the equations are everything that matters. The rest, yeah, I guess once you know the equations, you can do the rest too. Okay, or the algorithms, of course. Okay, any questions? One last administrative announcement. We'll put up a self-assessment test online, probably today or at the latest tomorrow. So that'll go up on, there'll be announcements on the Google News group. So if you haven't signed up for the news group yet, by all means do so. This is not meant as homework or anything else, but it's basically just meant as a self-test to make sure that you actually have the prerequisites to attend this class. So what you should do is go through those questions, and if you're running into trouble answering any of them, it means that you probably should make sure that you brush up on this area shortly, as in very, 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 very soon, as in over this weekend preferably. So if the self-assessment takes you many hours to solve, you should probably improve your background knowledge, right? And there'll be information about further of that stuff both online. We'll put maybe some videos up. The TAs will cover things. So, there's no point or no need in cheating because we will not assess this, right? This is self-assessment. So you check how well you do. What I would ask you as a favor, and actually in order to do yourself a favor, is if you run into trouble with any of those things, post online, and you can maybe post it anonymously or in whichever way, which subjects you would like to have covered in more depth, for instance, for the recitations of the TAs. Because until we go through the homework and so on, the TAs actually have a little bit of time to cover things on demand that will help you the most, right? So this is for your own benefit.
I was going to say, you want to do that ultimate by Friday.
Okay, so just such that it's also recorded on video. So please post those requests by Friday, because our poor TAs need to prepare, and it's better to ruin their weekend rather than their week, right? And given that the recitation is on Tuesdays, so please get this out by Friday, such that then the TAs can actually prepare and do a good job at, giving you a good overview. So this is really just meant as a supplement. If you notice that you're having trouble in a lot of the self-assessments, you should probably not take this course. So this is me trying to discourage you from taking my class, right? And Joe's class. But the point is, if you run into trouble for a lot of things, it's probably not in your best interest to take this course. So to give you a very stark example, last semester we had somebody who told me, Alex, your class is awesome. This d-dimensional calculus really blows my mind. That was very sweet of that person, but probably not in that person's best interest to take the class. Because if you're having trouble at d-dimensional calculus, you should probably fix that first before you do this. Okay, good. So without further ado, let's jump right in. And I promise in the future there will be not as long public service announcements in the beginning, but it's just to make sure that everything runs smoothly. And yeah, my office hours will be on from next Monday on. Okay. So just to give you a little bit of an idea of data sets of a reasonable scale, this is a really awesome graphic that I think probably Wade Johnston, who was born in 1962, at least I would infer that from his blog account, generated. And this is basically from last year the amount of data that is being generated in 1 minute on the internet. So let that picture sink in at some point when you look at the slides offline. But it basically means that there's crazy amounts of data that are being generated. So if somebody tells you about big data and they mean stuff that fits onto the memory card of your MP3 player, yeah, probably it's not big data. So gigabytes is not big data. Terabytes, single terabytes is not big data, right? Once you go beyond that, tens, hundreds of terabytes, you're starting to look at large data sets, and then once you need many machines, that's big data. So bear that in mind when you think about algorithms and how they scale. So an algorithm that runs into trouble with hundreds and thousands of observations is probably something that you can only use when you're dealing with medical patients and a very small sample. Okay. Most of the algorithms that we'll be teaching you will actually scale to big data sets. We won't necessarily always teach you all the techniques on how to really make them scale at crazy amounts, but they are scalable. Okay, good. So let's start with something very, very simple, linear regression. And this is really just a warm-up, and we'll get back to linear regression and classification next week. But just such that we have something usable to start with. So linear regression is basically just, you have some observations, and you want to find a linear model like f of x is a times x plus b, or in the vectorial case, it would be a transpose x plus b. And then what you want to do is you basically want to find coefficients a and b such that, for instance, the least mean squares distance between axi plus b and yi is minimized. And so how would you do that? Well, this is nice and infinitely differentiable and so on. So it's also convex. By the way, who knows what a convex function is? Okay, let me explain what a convex function is then. Okay, and this is the very simple non-mathematical definition. Let's draw the epigraph of the function. And it's a convex function if for any 2 points on that line, the function itself is below. Right? So in other words, if I have that f of lambda times x1, let's say this is x1, plus 1 minus lambda x2, so this is basically here, right, is less equal than lambda f of x1 plus 1 minus lambda f of x2. Right. Now, remember this when you need to work out this inequality. Obviously, this holds not just in one dimension, but it holds in general. And what you will get in general, if you were to plot the level sets of a convex function, then those level sets would also be convex sets. Now, when is a set convex? Well, that's very easy. Again, the same trick as here. I take 2 points, let's say at anywhere here. I draw a straight line, and any points on the line need to be within that set. note if it doesn't imply that, points outside this, if I extrapolate, they need not be in there. Another useful thing, just as an aside, a cone. I mean, we all know ice cream cones, right? They are pointy at one end and, well, as large as possible on the other end, at least the mathematical cones are. So I can basically take any point here, I extend a line from the origin through this point, and it will always stay inside this. And it's a convex cone if it's a cone and convex, right? That's the definition of a convex cone. Well, this one, for instance, would be. So your ice cream cone is convex if you extend it to infinity. Okay.
Would you draw a non-convex example?
Non-convex example. It's kind of hard for me to draw this, but it would, for instance, be something like so. If you look at it in profile, and then, well, basically take the ice cream cone, smash it on one side. You have a non-convex cone, still extended to infinity. So, yeah. So now this, obviously, if we set those derivatives to 0, we can see that we basically get linear equations in A and B. Right? So let's solve those. And the only thing that I'm going to do is I'm going to write this now with vectors rather than scalars. And just to make my life easy, because I don't really like to carry A and B around separately, I'm just going to extend x by x and 1. So by the way, this is a really useful trick that will come back many, many times over. We'll use the very same idea in the perceptron, so no effort here is wasted. So if, in other words, if I have a 10-dimensional vector x, and I want to have a constant offset, then I turn this into an 11-dimensional vector, where I have this 10-dimensional vector, and that one coordinate, extra coordinate, the 11th one, I set it to 1. Right? And then, now you need to solve this optimization problem here. Taking derivatives for vectors just works the same way as it worked for scalars. You have to be a little bit more careful about log determinants and so on. And if you guys want, we can cover some of this in the recitation. That's not a problem. You just need to say that this is what you want. And anyway, so we take the derivative, and 1/2 squared, by chain rule, just turns into 2 times 1/2. So this is why we had the 1/2, that it goes away there. So we have w dot xi minus yi times then the derivative with respect to w, which will just give me xi bar. Those are these guys here. And so then we need to reformulate in order to solve. And so let's just write it out. So we have sum over I. And since this is all linear, I can actually pull this inside. So I have w transposed xi times xi transposed, right? Well, okay, let's just write it like so. And I have this minus xi transposed yi. This has to be 0. So then this is equivalent to w transposed sum over I xi xi transposed. This is now a matrix. Right, this is d plus 1 times d plus 1 equals sum over I xi transposed yi. And then all I have to do is I have to take this matrix here and invert, right? And then we can solve for w. So what we're now doing is basically just very simple linear algebra. Yep?
So should it be like yi times x transpose? Like
So this is, it's actually a symmetric problem, right? So if I were to transpose this, right? And this equality still has to hold, right? So yeah, let me explain. So so this is an equality If I transpose it, it still has to hold. It doesn't change anything. So transposing this part here leaves it the same as the symmetric matrix, right? So what happens, though, is that the W moves over to the right-hand side. So let's do this, right? So we get W. And here, transposing this, since this is a scalar, this is a vector, just gets rid of the transpose. And voila, we have the equation here. Right. And then, well, all we have to do is just solve, right? And this gives us W equals sum over I xi transposed inverse sum over I yi xi. That's it. It's very straightforward. Okay. Any question about this so far? Yep.
Is W a vector here?
Yes, W is a vector here because, well, this first construct here is a matrix. This is a vector. So, in other words, it looks like so. Square matrix times vector. Bonus question, what if the y's are vectors? What does this block, what do those two blocks look like then? Any ideas? Okay, so if the y's are vectors, so right now they're scalars, right? We're doing scalar regression. Suppose I want to predict, let's say, for instance, the weight and the age of a person at the same time. So I have two-dimensional y's. So each of the y's is a two-dimensional vector. What does this object then look like? It's a matrix, exactly. So in that case, it would look like so, right? And so W would then also be a matrix. This part here doesn't change. So what you've just done is, by means of, well, drawing pictures, is to solve the d-dimensional linear regression problem. This will perform sort of okay, and we'll see in a moment actually what can possibly go wrong with this. Does anybody have any ideas of what could possibly go wrong with inverting this matrix here? It can be singular, exactly. So when can this happen? When might it be singular? Yep.
If our data are not independent from each other, if we have multiple same data.
If we have multiple instances of the same data, that can lead to a problem. It need not lead to a problem, though, because let's say we have 10 dimensions and I have 1 million observations, and some of them are linearly dependent of each other, then that's not a problem. However, if I have 1 million observations and they overall only span an 8-dimensional space, then I have a problem. Very good answer. Okay, and we'll actually run into problems of that form in a moment. What's a lot more insidious is that sometimes the eigenvalues will be just really small. Okay, and if I invert it, then the inverse of those will be really large. Other bonus question before I move on. If you look at this matrix here, what are the eigenvalues? Can you tell me something about them? Are they all positive? Are they all negative? Are they positive and negative? Any suggestions? Who votes for all negative? Nobody. Who votes for all positive? Who votes for arbitrary? Okay. So I think that, well, you're a brave soul. Thanks for being the devil's advocate here. Well, they are actually all positive. They're all positive because, well, actually we can check it, right? What we can do is, let's just take some vector. Well, here's a simple way to check it. Right, so if I have some matrix M, I want to make sure that all the eigenvalues of M are greater or equal than 0. All I have to do is just X transposed Mx has to be greater or equal than 0 for all X. Actually, let me call it V, because otherwise this will mess things up there. Okay, so let's check it. So V transposed sum over I xi xi transposed V. This equals, I can pull the summation out, sum over I V transposed xi times xi transposed V. Now those two terms are the same, right? They have to be, because, you know, transposition doesn't change anything. So this is nothing else than the sum over I V transposed xi squared, which is clearly greater or equal than 0. So what we just proved is that this matrix here has eigenvalues that are all greater or equal than 0. Okay. Yes, we will actually use that very same reasoning later on when we do kernels. So that's why I went through that in a little bit more detail. That's why I said greater or equal than 0. So it's positive semi-definite. Yes. So you could get very good comment. So you can get 0 eigenvalues, especially in the context where you have, you know, some subspaces where no data lies in, right? So if, for instance, the data lies in a plane, and then in this direction here I will have 0 eigenvalues. But I will have non-zero eigenvalues there. Right. Okay, so let's actually put this to good use. Now let's go beyond linear regression, which, by the way, will get you very far if you have very high dimensional data. Let's actually do something nonlinear, because this is more fun, right? So I could, for instance, use quadratic functions. Well, how do I get a quadratic function? Well, rather than 1 at x, I take 1 x and x squared. Well, I get a cubic function if I have 1 x, x squared, and x cubed. And I can go on and on and on. So in general, I will have, for a nonlinear model, f of x is w dot, and then some features of x that I computed. And I'm doing this explicitly here. So if I want to have something quartic, well, I'd have 5 times here. So nothing particularly special. So let's solve this, right? So remember, this is what we had for linear regression. Now, the only thing that I need to do is query replace. Compare. The only thing that happened is wherever I had x, I now have phi of x. This is the only thing that I need to do, and now I immediately have nonlinear regression. Okay. And, you know, one of the nice things is that this will then, of course, also give me a w that lies in the span of these guys here. So I don't have to fill the entire space. Basically, I just don't compute anything in the subspace. So let's have a look at what happens if I want to implement this. So this is very simple pseudocode for Python or MATLAB. I just go and, you know, take my feature vector, my phi of x. I compute this for all the x's, and I just vectorize that. It's basically just x to the 4, x to the third, second, x, and then the constant. Yeah, this just makes sure it's all ones and that the dimensionality matches. And then this is how you solve for w. So in other words, those 2 lines will give you a nonlinear regressor that's actually not too far away from the state of the art. There's a slight problem in it, which we're going to fix eventually, but that's about all we need to do. So if we do this, then, you know, how do we test? Well, we compute phi of x on our test data, and we apply w to that, and that's it. Any questions with that pseudocode? This is about the simplest algorithm you can design. Well, one of the simplest ones. Everything clear?
How many people are familiar enough with MATLAB notation that this code actually makes sense to them?
Okay. fair, probably about 80%. So if you've never used MATLAB or Octave, I would suggest that you install Octave. Yes, you have a question?
Excuse me, when you're dividing the phi xx transpose times phi xx, all of that is a vector or a scalar?
Okay, so this thing here is a matrix.
So my question is, how can you divide something by a matrix?
Well, that's MATLAB's way of writing the matrix inverse. So this is just MATLAB being a little bit loose on the notation. So, but it's actually, there's actually something a little bit more interesting happening behind the scenes. That's probably worthwhile talking about. So if I have a linear system y, let's say w equals m times x. Sorry. Let's write it the other way around. Oh, actually, whatever here. Y equals m times x. And I want to solve for x. Then, of course, it follows that x is m inverse times y. Now, the way how you can solve this is by first computing the inverse of the matrix and then multiplying the inverse of the matrix by y. You can do that. This is sometimes way too costly if you only have one particular y for which you want to solve this. Because maybe for that specific y, the solution is much simpler, and you don't really need to compute the full inverse. So there are all sorts of really nice numerical tricks on avoiding to ever compute the matrix inverse, but just solve this linear system. And the MATLAB notation of x equals y divided by m does nothing else but tell MATLAB, by the way, solve that linear system. I don't really care about seeing the inverse of m directly. This is faster and numerically more stable. So if you have a lot of those systems to solve, basically a lot of x's for you, which you want to know the y's, then it is a good idea to compute something like the inverse. There are actually, depending on what the matrix looks like, there are Cholesky factorizations or other factorizations for those matrices. I don't want to go into too much detail here because it's basically numerical linear algebra. But usually, if you have code where at some point you've explicitly computed the inverse of a matrix, there's a good chance that your code is not efficient. So try avoid writing the following thing. Let's call m tilde equals inf of m, and then you write x equals m tilde times y. This is a bad idea. Don't do it. Unless there's a really, really good reason. Okay. But that was a good question. Okay. So let's just look at regression. Well, here's the one-dimensional, so the linear regression. Well, okay. I mean, the blue curve is what the data really looked like. The red line is what we get. Right? That's what you would expect. For d equals 2, bingo, we actually get something that works really, really well. And mind you, those points here were drawn by drawing points uniformly from that interval, and then computing the blue curve and adding some noise to it. Because otherwise, it's too trivial. For 3 dimensions, it actually still works pretty well, right? I mean, it's a little bit largish here on this end, but it actually, if you think about it, it interpolates at least as well as the 2 dimensions. So even though we fit the parabola with the wrong curve, it still does a pretty good job in the region where we see the data. Now let's continue. 4 dimensions, not so many bad things happen. 5, well, you can already see that the scale here gets really large, right? Now let's keep on going. 6 dimensions, it already starts oscillating wildly. 7, 8, you know, you can see very large function values here, 9. Stuff starts going wild. And then at some point, MATLAB or Octave will start complaining quite a bit. So what's going on? Does somebody have an idea why MATLAB is complaining? Yep? I only have 10 observations. That's true. So for 10 dimensions, for 9 dimensions or more, I should have a problem. Yes. But it's already starting to complain around here, right? So 8 by 8 matrix, rank 7. And I have 10 points, right? So what's going on? Why? As a matter of fact, you know, yeah, around here, even for the slightly smaller matrices, it will already get unhappy. But what went wrong? So what happens is that I'm mapping the data into this high-dimensional space, right? Which is like an 8 or 9, whatever dimensional space. And within that very high-dimensional, well, relatively fairly high-dimensional space, because we're just doing, you know, simple regression, the data doesn't really span the entire space. So we are getting exactly the situation that we talked about here, just that, you know, it's much more convenient to draw in 2 or 3 dimensions rather than 10. So basically what's been happening is that our covariance matrix that we computed doesn't have full rank. Now, this is exactly one of those situations where you get numerical instability and you get overfitting. So we saw that, you know, if you look at those pictures, you know, the functions really veered off to infinity on both ends in a rather drastic way, which is exactly what you expect from a polynomial of degree 9. You know, it'll go wild for large numbers. So what do you do normally if you have a matrix that has almost, you know, that is rank deficient, and if you want to invert it? What do you typically do? Any suggestions? Yep?
Decomposition of the matrix.
So decomposition of the matrix, that's the really clever and smart way, right? So you factorize the matrix and you then just throw away all the eigenvalues that are below a threshold. You solve for the rest. What if I'm not that smart? What's a lazy way to do it too? Well, somebody else? You add the identity to the matrix. You add a small epsilon to all the main diagonals of the matrix. Exactly. So this sounds like a complete hack, right? I mean, this way I can always ensure that the rank is full. However, it's actually more than just a simple hack. It turns out that this is actually a very principled method of getting, you know, doing model selection and controlling the model. Because what happens, of course, is if I add some epsilon, right? Let's just do this, right? So we have our matrix sum over I, xi, xi transposed. I'm okay. Thanks. Plus, you know, epsilon times the identity. So if I now multiply this by, you know, my sum over I, yi, xi, then I know that if I invert this, this is never going to be larger than the norm of the sum over I, yi, xi times 1 over epsilon, right? Because this is then a lower bound on the smallest eigenvalue. So I cannot get infinities for W. So the norm of W is this. And so I've just upper bounded this. So what this basically means is that I'm upper bounding the size of my parameter vector. We'll see in more detail how that happens. But basically, this is a way of making sure that I don't have a too complicated solution as we move on. Okay. So we saw actually a couple of interesting things here, and this will be a continuing thread throughout this class. We saw underfitting. This was the case where we had, you know, the parabola and we fit it with a linear function and we got an awful fit. We saw overfitting, where the data was not, well, basically we didn't have enough data to really determine all the parameters. So in other words, the model was too complicated to fit the data. And we might have had insufficient confidence to really estimate all the parameters. Because even if you think about it, using a model, polynomial of degree 7 or 8, but if my data really only is a polynomial of degree 2, if I get enough data, at the end, at some point, I'll figure out that all the higher order coefficients are 0, and that only the first 3 coefficients are non-zero. Right? I'll, eventually figure that out. I just need more data. So the other thing that we saw is that if you recall the situation with d equals 3, the training error actually went down, and it kept actually, if you had looked at the numbers, the training error would have kept on going down further and further as we increased the dimensionality. But the functions got more and more crazy. So this is exactly the situation where if we look at the training error, so let's say here's model complexity. So we have 1, 2, 3, 4, 5, and so on. And here we have error. Then, well, it would have been fairly high here at training time. Then it would have gone down here, down there further. Would have kept on going down. Possibly at some point it might even have reached 0. Not necessarily monotonically, but typically it would. So we got something like this for the training error. However, our error then for new data, okay, sure, here it would have been high. It would have gone down, maybe there the lowest, and then it would have gone up again. Right. So the test error would have probably behaved like so. And so what you want to do, and this is part of what we will teach you in this class, is to figure out how to find the sweet spot here easily. Okay. So one way of finding this is actually very simple. You just go and set some data aside, and you look at how well you do on that set aside data. It's called a validation set. And there are fancy ways of doing this. But this is basically a very simple, straightforward way of doing model selection. Okay. So this is why the slide is green, because this is actually really important. It'll come back over and over and over. And this is just scratching the surface. Any questions so far? Okay, good. And let's move on to something with more equations. Density estimation. So this is Mr. Emmanuel Parzen, and he's one of the people who I think came up with this. So let's say, and I'm assuming that you guys are familiar with Bayes' rule. Who's heard of Bayes' rule before? Okay, good. Awesome. So I want to do density estimation. Why would I want to do density estimation? Well, because I want to, for instance, find out whether there are unusual observations. Because unusual observations are usually those with a low density. I also want to find maybe typical observations, prototypes. So you might care about this, for instance, if you, let's say you run a website, you want to find out what your target audience is. In this case, you might want to find the most prototypical users who come to your website. So that's what usually then you do, and then you go to an advertiser and say, well, yes, look, I have the perfect website for soccer moms. Won't you want to, show some ads that are suitable for soccer moms on it, like, let's say, minivans? Then the other thing that you can do if you do density estimation is, well, you can, build a classifier using Bayes' rule. Because, well, let's say I have x, I want to get y from it. I can compute P of y given x by taking the ratio of the joint distribution over x and y divided by the distribution over x. Now, if I have two classes, I can write this out as P of x given y times P of y divided by, the sum over 1 and minus 1 over these terms. So in other words, if I have a device that will give me p of x, and it will give me p of x for any of those class labels, I immediately get a classifier. You can also do regression with it, mind you, but then it gets a little bit more interesting what happens in the denominator. But this is essentially, a very simple estimator. The reason why I'm introducing this here is because it looks very different from what we just saw before, but it actually turns out that the regression estimator that we saw before can also be coached in the framework of p of y given x. We'll see that when we look at Gaussian processes. That'll probably happen quite a bit later in this class. Anyway, so one of the key tools in this context is we want to get p of x. Okay, all clear here? So let's just do something very simple. Let's say I want to find out what, the nationalities of, the people coming to my website, for instance, are. Or maybe I want to find out what your mother tongues are. Okay, so I go and, record, and maybe, just let's say, I look at the gender, look at what the mother tongues are, and then maybe, there's only maybe one woman who speaks Spanish and no man. Okay. And this is obviously not a computer science class because it's very well gender balanced. But anyway, so what I could do is I have, 25 observations, and then I divide by 25, and, I get those numbers. Okay. So these would be estimates of, the gender. And so the question is, well, what's going on here, right? So it's clear that there are not many Spanish speakers here, but maybe this is a little bit too drastic to assume that no male Spanish speaker would be in the room, right? What simply happened is we don't have enough data. Now, this is still kind of okay here because you could just say, well, let's take a larger class and so on. But what really happens is that, if I have, this discrete random variables, the number of bins really will grow exponentially in the number of, possible things that you could have. So for instance, if you run a website and you think, okay, well, I have 1 million visitors, I can really know everything about everybody. As soon as you start sharding by zip code, these numbers will go down drastically. Now then you shard by day of the week, operating system, gender, maybe the encoding, maybe their browser identity, maybe their device, and so on and so on. And you will very quickly get lots of empty bins. So in other words, even if you had 1 million visitors, you end up with lots of empty bins, and it's quite useless. So what's actually happening here is what's called the curse of dimensionality, namely the number of bins that I need to do anything useful grows exponentially with the number of dimensions. It gets even worse for continuous random variables, like let's say we have income, bandwidth, time spent on a site, and so on. So what really happens is you might have an underlying density that looks like so, but you get that kind of data, right? So, if we do something like 10 bins, you would say that's probably reasonable on, in one dimension. So with 10 bins, I mean the following thing. Let's say we have, from 0 to 1, I have 0.1, 0.2, 3, 4, 5, 6, 7, 8, 9. Okay. Yeah, they're not quite equidistant, but they should be. And I just count number of observations in each of those bins. And then I get like a piecewise density that maybe looks like so. Right. And so you might already wonder, well, is this really the best thing that I could do? Maybe it's a much smarter thing if I was to do something like so, right? It might be something that feels intuitively a little bit better. So the question is, can I actually get this? Well, as a matter of fact, you can. And that's what we're going to do. Now, if I have, 10 dimensions, which is not unusual, then I get 10 to the 10 bins. In other words, I'm screwed. So remember, this is what we started with. this is what we get, right? So we draw from that, and that's actually a lot of data for one dimension. And if I do bin counting, then, well, that's the result. And that just looks so much awfully worse than what we started with, right? So here's what we do. We basically, rather than taking just delta peaks at each location where we observe something, we just smooth things out. So in other words, if we have an observation here, then we don't just say, well, it has probability mass, it's basically a delta distribution here. Instead of that, we smooth it out and say it looks like so. And if we have another observation here, we'll do the same thing. We'll smooth it out, and it looks like so. And then you add those two things together, and you'll get something that'll look probably like so. Okay. No, actually, it should look symmetric, but fine, whatever. I guess you get the idea. So if we have then 100 observations, well, we take 100 of those bumps, add them up, divide by 100, such that it integrates out to 1 again, because we need to have probability of 1 overall for the set. And that's it. So you can pretty much plug in any function kx that would do the trick. Okay. Any question about this so far? So here's the magic equation. I get p hat of x is 1 over m, I equals 1 to m, k sub xi of x. So these are just, kernels that are centered at xi. And this will give you a very nice nonlinear density estimator. Now you can pick all sorts of different smoothing kernels, and you can write beautiful theory papers about which of those kernels is good. My suggestion is use a Gauss or a Poneshkov. This one has compact support, this one doesn't. But other than that, it doesn't really matter very much what shape the kernel has. What actually matters is the bandwidth. So let's just see how this works in practice. So, here's the data. Here's a density estimator. This is what I get by just taking this data. Okay. And here's the amazingly complex piece of MATLAB that will generate this. So this is your 2-line density estimator that you can implement that will produce something that's pretty state-of-the-art. Okay. So all this does is it just goes and computes all the distances to a set of reference points, right? And then my density is just you divide by the sample size, you normalize because this is d dimensions, and then here you have the Gaussians, right? So this e to the minus 1/2 distance squared divided by sigma squared. That's it. Any questions so far? Yep. Why do I want to do smoothing? Because, good question. Because let's say I want to, let's say this is my training data. Maybe this is the age of some users in an old age care facility, or maybe it's the weight of people in kilograms. I don't really observe anybody, let's take the weight. I don't observe anybody at 80 kilograms of weight, but then somebody else comes along, and I want to find out how unusual that is. Let's say you're a medical doctor, then of course you're in trouble if you can say, well, look, 80 is completely biologically implausible. You have to be either 82 kilo or 71 kilo, right? That's obviously not what you want. You want to be able to tell that person, well, 80 is probably quite typical. So that's why you want to do smoothing. Or in more than one dimensions, it gets just really hard, and you will, in most cases, say either, well, the likelihood that you see this person is infinity or it's 0, and neither of those are particularly useful answers. Yep?
The red line should be 9 to 9.
this one here, 10 to the 9? Well, if I have 10 dimensions, right? And each dimension contributes 10 bins. Then I have 10 times 10 times 10 times 10, so it's 10 to the 10. I will get 10 to the 9 if I had 9 dimensions.
I think he's asking compared to one dimension, it's 10 to the 9 times smaller.
Yes, yes, that's true. Compared to one dimension, it's 10 to the 9 times smaller. Yes. Okay, I'm sorry, that's true. You're paying very well attention. Thank you.
So in high dimensions, you get more and more active bins.
Correct.
Yeah.
So basically, in high dimensions, bin counting is a really bad idea.
That's why I say it requires high accuracy.
Well, you need, yes. So, well, you would basically need crazy amounts of data to actually do this reasonably well. And bin counting is just a really bad idea there. So this is just really, you know, reductio ad absurdum. So I'm just turning this into, you know, showing the crazy things that would happen if you were to do this. Okay, so let's have a look at what happens. Right? This is really, really simple pseudocode. And it will actually give you something that's pretty close to state of the art. Yep?
Are the x's normalized?
They don't have to be normalized. And so what could happen is, in fact, that if I get the scale wrong, I run into trouble. Right? So this is what I'm going to show you here. So let's say we get the scale a little bit wrong. Well, it doesn't look too bad, right? It's not too bad. So this is basically, yeah, this is for a Laplace kernel. So this is actually if I have the same scale, but a different kernel. Remember, the Laplacian was the exponential decay on both ends. The Gaussian was, you know, just, you know, Gaussian. Now, okay, let's say we take a Laplace kernel with lambda equals 10. So I use a bandwidth that's, you know, 1/10 the scale. And I get something that looks really horrible. It's probably going to not perform very well as a density estimator. So to summarize this, well, basically getting the size of the kernel right is really important. So this is just looking at different scales for the same data, what you get as a smoother. And this is, of course, what we would have wanted to have. So you can clearly see the scale matters a lot more than the shape of the kernel. So, well, if I have one that's too narrow, it'll overfit. If I pick one that's too wide, it'll, you know, just make everything flat. So how do we really choose this? And let me just show you one of the problems that happen if you do this naively. So let's say I have some observations here. And if I take a kernel, and if you think about this, you know, I have the r to the minus d dependence here. Because I need to make sure this integrates out to 1, right? So that's basically my scale. This is the offset. It's centered at xi. And that determines, you know, how wide or how narrow the kernel is, right? So if I make the scale narrower, then the kernel will get more peaked, right? If I make it very narrow, it'll get very, very peaked. It's probably not drawn to scale. But what basically happens is if I let r go to 0, the density estimate at the points where we observe things goes to infinity. So if I therefore was to go and compute p of x, you know, p of all the observations, by the product I going from 1 to m p hat of xi, this will go to infinity for r going to infinity. Okay. So this already tells us that using the likelihood on the data itself is a recipe for disaster if I want to, well, basically adjust the kernel width. Does anybody have suggestions of how to fix this? That's a really good idea. So you could basically compute the density estimate on a subset of the data and test on the rest. And that's exactly what we're going to do. And as a matter of fact, for Parzen windows, there's a very simple thing that we can do. Namely, we can just hold out one observation and train on everything else, and then test on that one guy. And we do that for all the observations. This is what's called a leave one out estimate. So this way, you're making maximal use of all the data of everything but one. So it's basically at an operating point that's very close to reality. Yep?
How do you know that your density estimation is right when you have the data?
So, well, this is exactly, for instance, what a holdout estimate might give you. And it might not give you, so, I mean, of course, you could get unlucky. And then what you can do is you can actually develop a fair amount of theory of proving that with high probability, the estimates that you get by holdout estimates are going to be close to the estimates that you will get on real data.
So I think he may be asking, why is checking the likelihood on a held out data set a good thing to do, right? And so if you do a good job estimating the if you do a good job estimating the density, right, then so let's think, suppose that I am able to give you a density which is high on some new data. Well, I didn't see the data before, right? So the only way I'm going to be able to say that the density is high on data that I'm actually seeing in the future is if I happen to get a good estimate of the density. And the better I do at estimating the density, and also the tighter the density is, then the higher my likelihood will be, right? My estimated p hat of x new will be, right? And so checking the likelihood on some new independent data is a decent way to figure out whether you have done a good job estimating your density.
So if we have some time, we might actually at some point do a little bit of information theory. But for those of you who might have taken an information theory class before, the entropy is actually going to give you the lower bound on how well you can do in estimating the density. And so the discrepancy between this lower bound and what you will achieve is going to be the Kullback-Leibler divergence between those two distributions. So if none of this makes any sense to you, relax, we'll get there. If you've taken an information theory class, it might help you make a little bit more sense out of what we're doing. So let's look at model selection in detail. So what we really don't want to do is, do the maximum likelihood fit where, obviously the densities will get more and more and more peaked as I make the, bandwidth narrower, and so I end up overfitting. And I won't be able to tell. Yep?
Someone here has a question. Maybe they have.
Oh, okay. Thanks. So who? Oh, yes.
Yeah, now this is quite a few slides ago by this point, but
Okay.
in the previous section, can you clarify what the axes were in your graph, represented in your graphs, and were we looking at one-dimensional data when we were estimating density?
Oh, so what the axes were for the one-dimensional density, they were arbitrary units. They meant nothing special. It's just that, I need to define it on some domain. So if you will, they were from 0 to 1.
The x-axis was your data, and the y-axis was the probability that you assigned to your data.
Okay, thank you.
So here's what happens with overfitting. This is, the data. These are the likelihoods, and it just gets really, really bad, right? Because you basically get something that's huge for wherever you see the data, and something that's essentially 0 whenever you haven't seen that observation. Underfitting's not good either. So what we're going to do is we're going to use exactly holdout data set. So the log likelihood, so that's the log, and I'm already averaging this by the size here. So sometimes people, I think, call it the perplexity is basically just, okay, actually let me derive this, because this is too many jumps at once. So remember, P of x prime given x would be the product I going from 1 to n prime P of x prime I given, so P hat of these guys. So basically I'm using x to generate my model, and then I'm computing x prime. And actually I should write it like so, because it's not really conditioned. So then I can go and compute the log of this. And that's simply because I usually don't like products. Sums are much nicer. So log of P sub x of x prime is just the log of the product of all these terms, which is nothing else than the sum I going from 1 to n prime log of P sub x hat of xi prime. And now dividing this by 1 over n prime, I'm going to define this to be, the normalized perplexity of x prime given x. So from learning theory, you could use this to, avoid having to use basically this type of model to figure out what the right parameters are. But what we can also do is we can simply measure it. So basically you can use math and theory to get the bound between what you're empirically seeing and what you expected to see. Or you can just compute it empirically. And the sad story is that even after a couple of decades of doing theory, the empirical version is still pretty darn hard to beat. So, and it's also much easier to implement. So for the purpose of 10701, use the empirical averages. Okay. Right, because, well, this is hard. The problem is, however, if we do exactly this, this is really wasteful, because we basically end up, holding out some data that we could otherwise have used to build our model. So the idea then in cross-validation is we use almost all the data to estimate the density and use a single instance to estimate how well it works, and then we average over it. So because if I was to just take one guy out and then use everything else, this might have huge variance. So what I do is I basically just sum over these terms. Okay. Now, the good thing for Parzen windows is that this is super easy to compute. Remember, P hat of x is 1 over n, sum over I going from 1 to n k of xi minus x. Or x minus xi, doesn't really matter here. Right? So if I was to leave one guy out, so P hat of x without some xi, xj of x is 1 over n minus 1 times sum I going from 1 to n. I is not equal to j, k of xi minus x. So I can easily express that in terms of p hat, right? The only difference is that we left the function k of xj minus x out. So I can write this as n over n minus 1, because I need to change the normalization of p hat of x minus, now I need to subtract exactly that term, namely minus 1 over n minus 1 k of xi, sorry, xj minus x. Okay. Is everybody comfortable with that derivation here? So that's exactly what we have written here, right? Now, the nice thing is that if I then evaluate this at location xj, this just becomes this p hat of x minus 1 over n minus 1 k of xj minus xj, so k of 0. Okay. So what this does is it basically takes the usual density estimate, and then it just subtracts the self-contribution of that one point. Everything okay so far? Any questions? Yep. This k function is exactly, this Gaussian or Eponichkov or, hat kernel or support that we saw a couple of slides before. Yeah, this is this guy here. That's the k function. Any one of those will do. And they have slightly different properties in theory, but in practice, they all work actually very similarly. Okay. Okay, good. So let's see how that works in practice. Yes? Sorry, what?
The first formula on that side on the left-hand side.
Yes?
Where it says given x2, x
So this basically just, yeah, okay, I would actually have had to use curly braces here. Yes, so I was sloppy and didn't use curly braces, but it's basically all the data set without the xith observation. Yes, otherwise it's not well defined, right? Unless I overload the operator. Yep.
There it says k of xi, comma, xj. There, in the right side, it says...
Yes, there's a typo. Thank you. Thank you. I need to fix this. Thank you. That's great. This is one of the reasons why you should download the slides afterwards. So slide number 42. xj, xj. Thank you. Any other questions? Okay. Well, so let's actually see what happens in practice. So this is exactly what we derived. Then I took the log, and then I just take the sum over all the i's and average. Okay. It's basically the average holdout log likelihood. So let's see what happens here. So this is now the same data that we had before, and I go and actually plot this. Right, just plot this score. And what we'll see is it peaks around here, at a scale between 1 and 10 somewhere. And this is also where we saw that, this would be a good fit, and that's what you get. So I deliberately used a different kernel from what generated the data. So I picked the Laplacian kernel, and I think the optimal number where this peaks is around, 2.3 or whatever. But basically, it doesn't look too bad. This is not the density we started with, but it's a close enough approximation that will give you decent log likelihoods. So to summarize, what we had is basically cross-validation. Now, k-fold cross-validation is if you don't just leave one guy out, but basically you break the data into blocks of 1/10 of the data set. And you leave 1/10 out, you build a model on the remaining 90%, and then you average. The reason why you might want to do this rather than leaving all but one out is that for many estimators, doing what I just showed, where you just leave one observation out, is actually computationally very costly to do. So if you do a 10-fold cross-validation, your code will only run 10 times slower, but you'll get a good error estimate. This is usually an acceptable price to pay in many cases. because computer time is cheap relative to engineering time, at least within reason. If you're running more than 1,000 machines, it's a different story, but yeah. In general, sacrificing a factor of 10 to get accuracy is okay. And so you basically, again, do the same thing. You just compute what the scores are. Basically, how well, you take some measure that of goodness that you care about. You evaluate that using on the remaining 10%, using 90%, and you use another 10% each time. You divide by 10, and that's a good estimate. This is almost unbiased, but the thing is that it's basically for a slightly smaller data set. Yep.
What about the bias of the leave one out customers?
So the leave one out has a bias of, well, basically a data set that is of size 1 over n minus 1 relative to 1 over n. So in terms of bias, leave one out is actually the best. But it's sometimes very costly. The other thing is, so what you would usually expect is that as you get more data, the performance of the system improves. In other words, your error will go down, right? And let's say this is 100%, right? Then by tenfold cross-validation, you're going to evaluate your system at a 90% sample size, right? So if you squint, you would see that the 90% error might be a little bit higher than the 100% error. In other words, therefore, you will get a slightly pessimistic estimate of how well the system performs. And it might also mean that you're going to tune your parameters in a slightly too conservative manner. But that's actually usually not too bad. So in case of doubt, over-regularize rather than under-regularize probably. Because at least this will guarantee that things don't diverge if you go far away. So what I'm going to do now is I'm going to show you how you can turn this into a classifier, because we have about 5 minutes left, and I think that's all we'll really need for it. So there's something called a Watson-Nadaraya estimator. So let's just take base rule, right? So we can estimate, let's say for the class 1s and the class minus 1s, I can just estimate P of x. And I can also estimate P of x for the entire data set, right? And so what I get is basically this thing here, right? So I get P of x given y. So this is just my Parzen Windows estimate if I just only use let's say class 1. Here's what I get for everything. And now I also need P of y, and a pretty good estimate of that would be just the number of y's, let's say class 1, that I got divided by the total number. Now, removing the my's and removing the m's will give me something that looks like sum over yi equals y, k of xi and x, divided by sum over I, k of xi and x. So it's basically a sum over the kernels for class 1 divided by the sum over all the kernels. Question? Can you explain where we're going with Watson-Nadaraya? Well, we are going to build a classifier. So I want to be able to distinguish, let's say, apples from oranges. And so for that, I need to be able to get P of y given x. And P of y given x, by base rule, is that ratio. Right? And so this is a classifier where I don't need to run a complicated optimization algorithm, but so basically we're going to actually use Parzen Windows. That's what Watson-Nadaraya is all about. On top of that, it'll give you a pretty good classifier that's almost state-of-the-art, and that only requires like half a dozen lines of code to code up. So it's simple, fairly decent, and it scales sort of okay. Now, if we want to get a decision boundary, so we basically want to find out where we should, output y equals 1 as the preferred outcome versus y equals minus 1, I might want to take the difference between P of y equals 1 given x and P of y equals minus 1 given x. Right? Because where those two things are 0, that's exactly where I'm ambivalent relative to what I should output, right? So if you do this, you could basically just have, y times p of y given x plus the y equals -1 times p of times this expression. In other words, it simplifies to that expression here, which is quite nice because you now have the ratio between these kernels weighted by the y's and the kernels not weighted by the y's, which, if you look at it, is just a sum over all these terms j, yj, times now a local weighting. So if you look at this, this function will be probably largest when x equals xj, and the weights will be small if x is really far away from xj. So in other words, what happens is that we now get a weighted average over the labels to tell us whether something is of, let's say, class 1 or class -1. So let's actually show this in pictures. Right? So here are two classes. And then the Watson-Nadaraya classifier will do this. Right? And here exactly at the boundary, this is where it flips over from predicting class 1 to class -1. And here's the super complicated pseudocode. Right? This is actually the unnormalized version because I don't really need the denominator for it. But this is really, again, just computing the distances and then summing over, y times these. Well, this is for Gaussian RBF. So this is your two-line classifier, which is nonlinear, non-parametric, and if you have plenty of computation and, in the limit of infinite amounts of data, will actually converge to the optimal thing you can do. So if you don't care particularly about performance, this is actually one of the best things you can do. So everything else that we'll be doing in this class is improving on it to make it scalable, to make it efficient, to get some guarantees and have some more control. Okay. So just, well, being slightly ambitious, right? I mean, why should the y's only be 1s or -1s? We could do a regression estimator. Okay, so let's see what happens. This is our data. The green line is what you get by using Watson-Nadaraya for it. So in other words, we immediately, with very little effort, got a nonlinear, function estimator by just doing the simple ratio. So that's the entire magic. There's nothing else to it. So 2 lines of MATLAB code will give you a nonlinear regressor. With that, you can now already start attacking interesting machine learning problems. It's very simple, but it actually does work quite well. OK, I think we're out of time. So what we will do next Monday is, well, we'll probably do nearest neighbors, which is a very simplified version of that. And then we'll go on to a lot more fun things.